let me teach you the vertical motion which will make things super easy. For example, consider a ball present on the surface of the earth. Now you throw this ball in upward direction. Let the initial velocity of this ball is 10 meters per second. Here, let me discuss the upward motion of this ball. The first concept is that the initial velocity of this ball is maximum because when you throw the ball, you exert maximum force. The second concept is that the velocity decreases with the passage of time as this ball gains height. It is because of the air resistance and gravity. The third concept is that velocity becomes zero at a maximum height. Now the ball will fall down. Here, let me also discuss the downward motion of the ball. We know that the velocity of the ball at maximum height is zero. So in the case of downward motion, the first concept is that the initial velocity of the ball is zero. The second concept is that velocity of the ball increases as it falls down. It is because of the downward force of gravity. The third concept is that the velocity of the ball is maximum just before hitting the ground. For example, its velocity may be 10 meters per second. Therefore, remember that in vertical motion like upward motion, the initial velocity of the ball is maximum, but it decreases and becomes zero at maximum height. While in vertical motion like downward motion, the initial velocity of the ball is zero, but this velocity increases and becomes maximum just before hitting the ground. Now you must also learn the constant velocity in linear motion. Consider a ball present on the surface of a ground. When you kick this ball, it starts moving. Let the initial velocity of this ball is 48 meters per second. The ball covers some distance and finally it stops. This ball stops due to frictional forces like ground friction and air resistance. Now consider an ideal case. If we neglect the air friction and the ground friction, does the ball stops? The answer is no. No frictional forces mean that the ball will move with 48 meters per second at each and every point forever. It is an ideal case which is not possible in real life, but we study it only in physics. Therefore, we say that this ball is moving with constant velocity. Thus, remember that in absence of frictional forces, object moves with constant velocity. Now we can easily understand the projectile motion. Consider a ball. Let you kick this ball and it starts moving. We can see that the ball moves in parabolic path. I am interested to analyze the motion of the ball at this point. Initially, the ball is present here. Horizontally, it has moved to this point. But the ball is not present here. It is present vertically at this point. With respect to its initial position, we say that the ball is moving in horizontal direction as well as in vertical direction. Let me repeat it. The ball is moving in horizontal direction as well as in vertical direction. In physics, such type of motion is called 2D motion because an object moves in x direction as well as in y direction. Therefore, we say that the projectile motion is 2D motion. Now consider that the initial velocity of the ball is u is equal to 50 meters per second. Let the motion of the ball forms 20-degree angle with x-axis. What about the horizontal velocity ux and vertical velocity uy? Well, we know that ux is equal to u cos theta and uy is equal to u sin theta. The value of u is equal to 50 and that of theta is equal to 20. We get round about 47 meters per second. Thus, the initial velocity of the ball in x direction is ux is equal to 47 meters per second. Similarly, in the case of uy, put the value of u and theta. We get uy is equal to 17 meters per second. Thus, the initial velocity of the ball in y direction is uy is equal to 17 meters per second. Now listen carefully. The ball is moving in the air. the ball experiences two types of forces. For example, at this point, the ball experiences downward force of gravity and air resistance in this direction. At this point, the ball experiences force of gravity and air resistance. At this point, the ball experiences force of gravity and air resistance. As in ideal case, I neglect the air resistance on the ball at this point. I also neglect air resistance at this point, and I again neglect air resistance at this point. Let me ask you, how many forces are acting on the ball? Well, the answer is one. Only one force, the downward force of gravity, is acting on the ball. Therefore, note it down that only gravity acts on projectile. It means that there is no horizontal force acting on the ball. Thus, the initial velocity of the ball along x-axis would be 47 meters per second at each and every point. We say that the ball moves with constant velocity in x-axis direction. It is because no force is acting along x-axis. Now, what about the velocity of the ball in vertical direction? Well, the initial velocity of the ball in y direction is 17 meters per second. But as the ball gains height, its velocity decreases with the passage of time. For example, at this point is 9 meters per second, at this point is 5 meters per second, and finally, the velocity of the ball becomes 0. If you do not understand that y velocity of the ball decreases, then it is because ball wants to move in upward direction, but the gravity is pulling it in downward direction and thereby decreasing its velocity. Until now, we have learned that in projectile motion, an object like ball moves with constant initial velocity along horizontal direction or x-axis, while the velocity of the ball in vertical direction or y-axis decreases with the passage of time. Now let me analyze the motion of the projectile or the ball at each and every point, which will further strong your concepts. For example, at this point, the vertical motion of the ball is 5 meters per second and its horizontal motion is 47 meters per second. At maximum height, the vertical motion of the ball becomes 0, but the horizontal motion of the ball is still 47 meters per second. Remember that at maximum height, the motion of the ball is not 0 because the ball still moves with 47 meters per second in horizontal direction. Only the y component or vertical component of motion is 0. Now the ball will start falling down. At this point, the vertical velocity of the ball is negative 5 meters per second and its horizontal velocity is 47 meters per second. And at this point, the vertical velocity of the ball is negative 17 meters per second and its horizontal velocity is 47 meters per second. Remember that negative sign doesn't indicate the smaller value. It only indicates the opposite direction of the ball. Thus, we can analyze that as the ball moves upward, its velocity decreases with the passage of time in vertical direction, but its velocity in horizontal direction remains constant. At maximum height, the y component of the velocity is 0 but not the x component. Secondly, when the ball falls down, its vertical motion increases with the passage of time, but its horizontal motion again remains constant. To conclude the horizontal motion and vertical motion of the ball or projectile, we learn that the initial velocity of the ball ux is equal to u cos theta, like ux is equal to 47 meters per second, while the initial velocity of the ball in y direction is uy is equal to u sin theta, like uy is equal to 17 meters per second. Secondly, the velocity of the projectile remains constant along x-axis. According to Newton's law, when velocity is constant, net force in x direction is 0 and acceleration in x direction is also 0. In the case of vertical motion, firstly, velocity decreases. Secondly, at maximum height, velocity becomes 0. Thirdly, velocity increases. Hence, velocity is not constant in vertical direction, so the ball or the projectile experiences the net force of gravity in y direction. Therefore, it has gravitational acceleration negative g in vertical direction.
Hi, today I want to talk about projectile motion. So here's the setup. I'm assuming that I'm launching a projectile at some angle with respect to the horizontal, and the angle is theta. I'm launching the object at some initial velocity v0, and I want to look at the motion of this particle as it travels through the air. So the first thing we want to do is define a coordinate system. So I've done that here. So I'm going to call everything pointing up, that'll be in the positive y direction, and everything pointing to the right is going to be in the positive x direction. So when describing the projectile through the air, the key thing to remember in this is that things that are happening in the x direction are kind of independent from what's going on in the y direction. So we're analyzing the motion along each direction kind of independently. They're linked together by time, but still, we want to break things down and look at each component separately. So the first thing we're going to do is we're going to break the initial velocity down into two components. So let me redraw this initial velocity that's at some angle. The magnitude of the vector is v0, and our angle was theta, and that was defined with respect to the horizontal. So the first thing I want to do is I want to break that down into two components. So again, my coordinate system is defined by this x-axis and the y-axis. So I want to break things down into an initial velocity in the x direction and also some initial velocity in the y direction. Now, just by inspection, you should be able to write that the initial component of the velocity in the x direction is going to be v0 cos of the angle theta. And the initial component of the velocity in the y direction is going to be v0 sine of the angle theta. All right, now the next thing I want to do is I also want to write what is the direction of the acceleration everywhere in space. Now you have to be a little bit careful with this. So I want to write the acceleration. And if you remember, this is a case of uniform acceleration. So the acceleration is constant. It's always going to be in the y direction. And if I plot it anywhere on this dashed line, which represents the trajectory of my projectile, the acceleration is always going to point down. If I plot it near the top, the acceleration is pointing down. If I plot it near the second half of the trajectory, it's also pointing down. If I plot the acceleration right before it hits the ground, it's also pointing down. The magnitude now is going to be little g, and it's little g everywhere. And again, our little g will be, the magnitude will be 9.8 meters per second squared. So if I want to write the acceleration now, I really have to write it with respect to a coordinate system. You know it's pointing down. So if it's pointing down and it has a magnitude of 9.8, the way you write that now is going to be, it's going to be equal to minus little g. Okay, we're now in a position to analyze the motion because we know the initial velocity and I know the acceleration at every point in time. All I want to do now is I want to write expressions that are going to tell me the x direction displacement and the velocity, and also the displacement in the y direction and the velocity in the y direction as a function of time. So let's start with the displacement in the x direction. So I'm going to write it as x minus x0. So I'm starting from some initial position here, and let's just call this delta x. That is the displacement from the origin. So this here is simply equal to the initial velocity in the x direction multiplied by time. Now there's no other term for the x displacement because there's no acceleration in the x direction. The acceleration is only pointing down. That's in the y direction. The next thing we want to do now is also describe the velocity in the x direction. So in order to do that, simply the velocity in the x direction is going to be equal to the initial velocity in the x direction, and, well, that's it. There's nothing else to add. The equations of motion in the x directions are very, very easy to write because there's no acceleration in the x direction. So let's repeat the same exercise now for the y direction. It's a little bit more complicated in the y direction because there's acceleration. So we need to add a term that describes its effects. So the displacement in the y direction, which is y minus my initial position where I started, is going to be equal to delta y. And now, well, the displacement in the y direction, the first term looks similar to what we had in the x, except we'll have to plug in the initial velocity in the y direction multiplied by time. And now there's a term with acceleration. And if I factor in the sign, which is negative for this case because the acceleration is down, this term will simply become negative 1/2 gt squared. And the negative reflects the fact that my acceleration is minus g. Again, this is just the simple kinematic equation that gives you the displacement of an object that has constant acceleration. The last thing I need to do now is I need to tell you what is the vertical component of the velocity as a function of time. That's going to be equal to my initial component of the velocity, which is v0 sine theta that I have up above. And now there's also a term that describes the acceleration, and that will be minus the acceleration times time. So there you have it. We have equations that give us the displacements in both the x and the y direction, and we also have equations that give us the velocity in the x and the y direction. Okay, so I want to first analyze the motion, at least qualitatively. So let's first examine what's going on to the velocity as the projectile moves along this path. One thing we notice is, let's plot the magnitude of this initial velocity in the x direction. So we have a vector that's about this long, and that is the initial velocity in the x direction. So let me cut and paste this, and let's place it at different points along this trajectory. Well, what if we're over here at this point? That's the initial velocity. And you notice, if I look at my equation of motion down here that gives me the x velocity versus time, one thing I notice is that for every single time, this is my equation. It doesn't change. So what does that mean? That means that this vector over here is always going to be the same length. If I plot it over at this position, I get a vector that's roughly the same length. It's the same length, rather. If I plot it at the top, I'm going to get a vector that's the same length. So the velocity at every single point, at least in the x direction, is always the same. Even down over here, it's a vector that's the same length right as it hits the ground. The instant before it hits the ground, that's the magnitude of my velocity in the x direction. Now let's look at what's going on in the y direction. In the y direction, initially I have a vector that's pointing up. So I can go ahead and plot it right here. This is my initial velocity in the y direction. It's this vector here. Okay, and let's look at what happens as a function of time. Well, again, if you look at my expression now for the velocity as a function of time, I have an initial term, and now I'm subtracting another term here. So what does that mean? That means it's getting smaller. So my velocity in the y direction is a vector now that is getting slightly smaller as time goes on. As I near the top, let's have a look at that vector. It's very, very small, and once I'm right at the top, I can't actually even plot it because the component of the velocity in the y direction equals to 0 at the top. And then what happens? Look at this expression. After time gets beyond a certain value, the second term here is going to be bigger than my initial velocity term. So the term that has the gravity multiplied by the time will become bigger, and that means overall the velocity in the y direction will become negative. And for a vector to become negative, that basically means that I'm simply changing directions. So after a certain amount of time, this is what's happening. So the velocity in the y direction basically just switches sign and then becomes bigger with time. So it'll look something like that. At every single point in time now, since I know the magnitudes of each component, I can go ahead and plot the vector, Vy, as a function of time. Likewise for this one, I know both components of the vector. I can go ahead and plot the velocity vector. Right before it hits the ground, again, you're going to have a component in the y direction, and you can go ahead and plot the total component of the velocity, or the total velocity, which is going to be at some angle. Now it turns out that if you've launched this projectile at an angle theta, this picture is actually symmetric with respect to the center. The center, we said the velocity in the y direction is equal to 0. Actually, what happens now right before it hits the ground? Well, the x component of the velocity is simply equal to the initial one. That doesn't change. We know that's the same everywhere. So this vector at the start is equal to the vector at the end. However, the one in the y component basically simply switches signs. So if I had an initial velocity in the y direction that was pointing up and had a particular magnitude, right before it hits the ground, that vector is going to have the same length as the initial length, except it's going to be in the opposite direction. So opposite direction. Okay, so now let's look at things a little bit more quantitatively. We're going to look at the maximum height that the projectile can achieve, and we're also going to look at how far it could travel. Okay, so let's first start by finding the maximum height. Well, I'm looking for a y displacement, and I want to know when the y displacement is as big as you can get. Where to start? Well, we have an equation down here. This tells me the y displacement. So let's substitute that value there. The y displacement is, it's my initial velocity times time. Let's substitute the value of the initial velocity. That's v naught sine theta multiplied by time minus 1/2 little g times t squared. This tells me the height at every single time. If I substitute 0 here for time, I get 0. So yeah, that's because I started right here on the ground. So how do I get the maximum velocity? Well, typically you know the angle at which you threw the object. You know the initial velocity. You just don't know which time do I substitute into this equation. So for that, you have to look at what's going on over here at the top. What else do we know about the top? From the previous discussion, I said that at the top, you have something very special that happens. That the y component of the velocity at the top is equal to 0. Well, let's look at our equation now for the y velocity. That means that Vy equals to 0 at the top. That has to be equal to V0 sine of theta minus little g times time. So I have two expressions here. I have one that gives me my displacement, and I have another one now that I can use to figure out which time I should actually substitute into equation 1. So by solving equation 2, we get the time to go to the top. The time to go to the top now, again, I'm just going to isolate and, for the time and solve this equation. I'm going to get V0 sine of theta divided by little g. This is how much time it takes for the projectile to go to the top. Now what can I do with this expression? Well, if you go back now and you substitute this expression into equation 1, you're going to get the displacement, or the maximum displacement. So delta y max, maybe I should call it delta y, is going to be equal. Again, the only unknown in this equation is really that time. So if we substitute everything in, what are we going to get? We have v naught sine theta times time. The time also has a v naught sine theta. So this term here becomes v naught sine theta. All of this is squared divided by little g. Minus 1/2. My acceleration is little g. And now what do I have? Well, I've got t squared, which is, again, is this expression over here. Divided by little g. And I can't forget to square the whole thing. Now this looks very complicated. However, the terms look almost identical to each other. If you simplify this, you're going to get that the maximum displacement, or the maximum height that you're going to achieve, is going to be v naught sine theta. This term remains squared. Sine theta will remain squared. You're going to have 1 in the front minus 1/2, so you're going to be left with 2 times little g. So here's my expression now for the maximum height that my projectile is going to reach. So one thing you see is, when is this height the maximum? For any given velocity, how do I get the biggest vertical displacement? I'm going to get the biggest vertical displacement whenever sine of the angle theta is equal to 1. And when do I get sine theta equal to 1? That's when the angle theta equals to 90. That's if I shoot the object straight up, that's when I'm going to get the highest maximum height. Okay, and the last thing I want to look at today is the range of the projectile. And that's basically, how far is the projectile going to travel? What's the horizontal displacement of this projectile? Well, if I want to know the horizontal displacement of the projectile, I should use an equation that describes the horizontal displacement. So in this case, I'm going to want to know my horizontal displacement, x, which is what I'm going to call my range, because I want to find what the maximum displacement in the x direction is. And that's what I've defined by the green line here. That is simply going to be equal to my initial velocity in the x direction, which I know. It's simply v0 cos of theta multiplied by the time. So if I know an expression for the time, I could substitute it into this equation. Let's call it equation 1. And I can find what the range of the projectile is. So there's one more thing that I want to mention again that's very important about projectile motion, is that everything is symmetric about the top. For example, if you know the time it takes to get to the top, which we just calculated in the previous example, that means that the total flight time, the total time that the particle is in the air, is simply going to be twice the value it takes to get to the top. Let me write it down here. 2 times t top. So the total time, the total flight time here is going to be 2 times v0 sine of theta divided by little g. That's my total time. So that's really the only expression that I'm missing. So if I go back now, I can write that the range is simply going to be equal to v0 cos of theta. And I want to know the time. Well, I need to know the time right at this position, right before it hits the ground. That's the total flight time. So that's simply 2 times v0 sine of theta divided by little g. If you simplify everything, our final expression for the range, that's our maximum x displacement, is going to be 2 v0 squared sine theta cos theta divided by little g. And there you have it, folks. So this is the expression that we have for the range of our projectile. Okay, to summarize everything we've learned today, we've broken down our initial velocity into x and y components. Remember, the acceleration is only in the y direction. There's no acceleration in the x direction, and the acceleration in the y direction is the same everywhere. It's the same here, same there. Regardless of where you draw that vector, you have to have the same length in the same direction. To analyze the motion in the x direction, we looked at the x displacement and the velocity in the x direction. The velocity in the x direction is very easy. It's constant. It doesn't change because there's no acceleration in the x direction. Therefore, the displacement in the x direction takes on a very, very simple form. It's simply my initial velocity multiplied by the time. In the y direction, things are a little bit more complicated because I have to include the acceleration terms. And here are the expressions for the displacement and the velocity. We also looked at the top. The top's a very special point for projectile motion because the velocity in the y direction goes to 0 at the top. And if you solve the expression, you obtain that the amount of time it takes to go to the top is simply v0 sine theta divided by little g. And since everything is symmetric about the middle, that means it's very easy to calculate how much time it takes for the projectile to do the complete trip. It's simply twice as big as the time it takes to go to the top. Using both of these times, we're then able to find what the maximum displacement in the y direction is. And we're also able to find what is the maximum range that this projectile will travel.